So the next topic is dealing with complex numbers. Now this is something that we've dealt with in Math 171. One thing you have to remember is that the imaginary number comes from the square root of -1, or square root of negative numbers. And complex numbers, on the other hand, are part imaginary and part real. So we have this z, and z is just a common way of describing a complex number as a single letter. So we're going to let z represent a plus bi, where a is the real part and bi is the imaginary part. Then we're going to let this thing called z bar, and it's basically just a z with a little dash on top of it. We're going to let that represent the conjugate of b. And the one thing you have to remember about the conjugate is the middle sign does change. So if it was a plus bi is the original complex number, then a minus bi is its conjugate. Be careful not to change both signs. That becomes known as the opposite. All right, so why are we talking about complex numbers again? Well, when you learned them back in 171, you can easily add, subtract, multiply, and divide these things. But when we come up to things like 2 minus 3i raised to the 7th, then we're talking about something that's really complex to do as a complex number. It's really easy to do like 2 to the 7th, but 2 minus 3i to the 7th requires you to write out the binomial 7 times and FOIL many, many times, and distributive property way too much. And then there's another complex thing, like what if we want to take the cube root of this number? And that becomes not even calculatable in its current form. So both of them are not friendly to calculate, thus we need to change the way we see complex numbers. So the way we're going to handle a complex number from this point on is as a coordinate in a complex plane. So here we have the imaginary axis being the original y-axis, and that's where our imaginary numbers are going to go. And then we'll keep the x-axis as the real axis. So this one will be the real axis. All right, so if we do that, then we can change 2 plus 3i into a single coordinate, this point up here, 2, 3, and we'll let it represent the point 2 plus 3i. And notice it's 2 to the left and then 3 up on the imaginary axis. So that's where the 2 for the real part is coming from, and the 3i is coming from the imaginary axis up 3. So now that we've put the coordinate point that represents 2 plus 3i into a coordinate system, we can now change complex numbers into a polar coordinate. So we're going to call those complex numbers to polar form. And the way we're going to go about it is basically the same as changing any coordinate into polar coordinates. So the first thing I would do is, plot the point and then draw the line segment that goes from the origin to that point and draw a right triangle down to the x-axis. It's always going to go to the x-axis just like regular trigonometry. So we're going to label our sides, of course, 2 and 3. And then we're going to find the length of the hypotenuse. Of course, that's going to come from Pythagorean theorem. So we're going to have c squared equals a squared plus b squared. And then we don't know what c is. And a is 2, and b is 3. And we're going to get c squared is equal to 4 plus 9, which is 13. So c is the square root of 13. So this side gets called the square root of 13. Now, strangely, for complex numbers, that square root of 13 has a special name. It is called the modulus. So we can say the modulus of this complex number is the square root of 13. All right. Then we can find the angle, theta, here. And to find theta, we don't want to use the modulus. We're going to use the original sides. We're going to use tan inverse. So theta, is going to equal the tan inverse of 3 over 2, opposite over adjacent. And then, of course, plug that into a nice little calculator and get, in degrees, 56.3. Now remember, depending on the question, you might want it in radians. But for degrees, it is 56.3 degrees. So let's go back here. So the theta is approximately 56.3 degrees. And I know this is the right answer because it is in the first quadrant, and tan inverse works in the first and the fourth. So we can say as a polar form of this number 2 plus 3i, we can represent it with a modulus of 13. Oh, and by the way, even the angle has a fancy name. This one is called the argument. So we have an argument and we have a modulus. So when we write it as a polar coordinate, it's going to be the modulus first and the argument second. So this would be the polar form of the complex number. Then there is another form, and it's called the trig form. So from polar to trig. So the trig form is going to take on the idea that it's still 2 plus 3i, it's just now we're dealing with a modulus and an angle. So if I look at my picture again, and I'm just going to draw a little sketch here. And I know what theta is equal to, and I know this side is 3, and I know this side is 2. So remember, 2 up here was the x-axis moving 2 to the right, and the 3 up here was going along the y-axis, 3 up on the imaginary axis. So basically all we have to do is reconvert this 2 into 3 to represent by these two numbers, the modulus and the argument, the hypotenuse or radius of a circle and the angle of opening. So if we look at it as, sine and cosine, put this modulus back in here, or if we look at this as cosine and sine, we'd have cosine of the angle is equal to adjacent over hypotenuse, and sine of the angle is equal to opposite over hypotenuse. So if we solve for the 2 and the 3 in the original number, we would get 2 is equal to the square root of 13 cosine of our angle, and 3 is equal to the square root of 13 sine of our angle. And if you go back to, polar coordinates, this is the same thing as saying, it's the same thing as saying x is equal to our cosine of theta, and y is equal to our sine of theta. So when we're talking about changing a polar form into a trig form, we're actually going to use these formulas right down here. So if we write this out, and it's going to get a little weird, we're going to have 2 plus 3i, where 2 is the x and 3 is the y, is equal to the square root of 13 cosine of, and I'm not going to write 56.3 degrees, I'm just going to write theta, plus, and then this I has to be involved from the original number 2 plus 3i, so I'm going to put that next to the sign, so it would be square root of 13 times I times sine of theta. And of course, since both terms have the square root of 13, it's easier to write it as the modulus times cosine of the angle, 56.3 degrees, plus I sine of the angle, 56.3 degrees. And this thing, if you multiply it out exactly, would become 2 plus 3i. So this is what's called trig form. Now, polar form is nice to come up with, but trig form is the one that's actually more important. All right, so let's convert this imaginary number, negative 3 minus 5i, into polar form, which is generally the first step you have to make anyways, and then we're going to move it into trig form. So the first thing I would do is, if you want to try to do this without a picture, you're going to make some silly mistakes. So it's always better to have a picture available, at least a reference picture, not a perfect one like I'm going to do. So negative 3 minus 5i is 3 to the left and 5 down. So this coordinate right here is going to represent negative 3 minus 5i. Okay. So the rest of it would be, draw a triangle. And we're just going to label a few things about this triangle. And we're just going to label a few things about this triangle. This side is negative 3. This side is negative 5. This is the angle of the reference angle of the main angle. Let's call it alpha. So we can find straight marks. We can find the modulus of this complex number, modulus, and that's going to equal the square root of the real component squared plus the imaginary coefficient squared. You can also call it a component too. Just don't put the I in here. If you put the I in, it'll actually mess things up. So this becomes 9 plus 25, which is square roots of 34. So the length of this hypotenuse, also known as its modulus, is square root of 34. Then we're going to look for the angle. Now, the angle we're going to look for is not alpha, but we're going to kind of treat it as tangent inverse of opposite over adjacent. And let's just call this thing, beta. Now, I'm calling it beta for a specific reason. Tan inverse does not guarantee you get the right angle on your calculator. It gives you an answer, which is great, but it's not always the angle you want. So I'm going to call it beta. Negative 5 divided by negative 3. There we go. It's about 59 degrees. So this is approximately 59 degrees. And here's the reason I don't want to call this one theta. Theta is supposed to be the angle for the polar coordinate. But we're in the third quadrant here, and 59 degrees is over here in the first quadrant. And that's definitely not in the right direction that I want it to be in. I want it going down into the third quadrant. One thing I know for sure, though, is alpha is definitely equal to 59 degrees, because these two angles here and here are opposite angles, and therefore they're congruent. All right? But what I'm looking for is the measure of the angle that starts at the positive x-axis and wraps around down to here. Well, if alpha is 59 degrees, which is this angle here, and we're trying to wrap all the way around to it, that's 180 degrees and then past it. So theta, the angle that we really want, is 59 degrees plus 180 degrees. So this is 239 degrees. So the polar form of my complex number, oops, let me back up here, negative 3 minus 5i, it gets converted into the polar form of square roots of 34 and the angle of 239. And just again for labeling purposes, the square root of 34 is called the modulus, and the 239 is the argument. Okay. Now, if we want to take the modulus and argument and create trig form, then negative 3 minus 5i is literally equal to the square root of 34 cosine of 239 degrees plus I sine of 239 degrees. And what's good about this is these are literally equal to each other. If we distributed square root of 34 to these two pieces, we would get negative 3 minus 5i, but not necessarily exactly. So let me show you what I mean by that. And when we type this in our calculator, it gets us really close to negative 3. It's not exact. And that's because the 239 degrees that we calculate here was rounded from that reference angle of 59 degrees from the calculator. 39 degrees we'd get really, really close to -5, but it's not exact. And the same reason applies is because we're using a rounded value. Now, this next part, I just wanted to show you how multiplying trig forms works, and what it'll lead to is a shortcut. And then I'm going to have a shortcut of the shortcut. So if you want to skip this part, great. If you want to see why this thing actually works on the next few minutes, then pay attention to this. It doesn't take too long. So the first thing we're going to do here is we're going to be using a lot of these product to sum formulas that I have over here to the right-hand side. So, they go together like this. I just couldn't fit them all in one line. This, I stole it from the final exam formula sheet for 171. So when we FOIL this out, we're going to get cosine of alpha, cosine of beta, multiplying the first. And then we're going to do the outer, which will be cosine of alpha times I sine of beta, and the inner, which will be just reversing the letters. So we're going to get plus I cosine of alpha sine of beta, and I'm going to write it right underneath it the other one, which is sine of alpha cosine of beta. And they both have the i's. And then when we do the last one, we're going to get I squared. Remember, I squared is equal to -1, so we're going to get minus sine of alpha sine of beta. All right, so let's take care of these in pairs. So the first pair I want to look at is the first term and the last term. So cosine of alpha, cosine of beta is kind of like cosine x, cosine y. So we're going to get 1/2 cosine of x plus y plus cosine of x minus y. And then the other one is going to be the opposite of sine alpha, sine beta. Well, sine alpha, sine beta will be this formula. And then we're going to have this equation. So if you take these two equations and you basically are going to change the signs of the cosine x minus y and the cosine of x plus y, what's going to happen is these two are going to be positive, this one and this one, and these two are going to be opposite signs. So these two are going to just cancel out. So you're going to get 2 cosine of x plus y, and then half of that will bring you back down to cosine of x plus y. So when you add these two together, you're going to get cosine of x plus y. All right, change colors. Let's go with orange. Now the I terms, these two guys, and the reason I stacked them is because they go together anyways, are going to relate to the other two formulas. So sine alpha, or cosine alpha, cosine sine is this guy, and sine cosine is this guy. So if we look at those two formulas, and all we're going to do is add them together, you'll notice right off that these two terms are going to cancel. And then you're left with 2 sine of x plus y, and then half of that will be just sine of x plus y. So you get plus I sine of x plus y. So when you're multiplying complex numbers in terms of their trig forms, at least the trig part, you're just adding the angles. This is called De Mornay's, I hope I spell it right. It's probably wrong, theorem. So De Mornay's theorem says when you're multiplying trig forms of complex numbers, you just have to add the arguments. You're still going to multiply the moduluses. So if you have, square root of 2 times times cosine of 10 degrees plus I sine of 10 degrees times 5 times cosine of 15 degrees plus I sine of 15 degrees. Then when you multiply these, you're going to multiply the moduluses together. So you're going to get 5 square roots of 2 times, and then the angles you're going to add. So 10 plus 15 is 25. So our final answer is this. So if they're in trig form, it's really easy to multiply two complex numbers. Don't even have to FOIL. Just have to add the angles and multiply the moduluses. And all of that from the product to sum formulas. I find it much easier to convert everything into Eulers formula, which I'll tell you what it is in a little bit, than to do things by de Mornay's theorem. De Mornay's theorem, you have to memorize a few things to make it work throughout, where Eulers formula, it'll just become natural. So what is Eulers formula? Well, Eulers formula relates an exponential function to represent the trig side of a complex number. So we get this cosine theta plus I sine theta can be simply written in Eulers formula as e raised to the I theta. So this makes life a lot easier. For instance, if we go back to the cosine of, if we go back to cosine of 10 degrees plus I sine of 10 degrees, and we multiply that by sine of 15 degrees, cosine of 15 degrees, plus I sine of 15 degrees. If we change both of them into Eulers form, then the first one is going to become EI to the 10 degrees. And the second one is going to become EI 15 degrees. So it's actually kind of writing it in terms of polar form, dropping the sine and the cosine. Now, what's interesting about this is when we multiply these e's together, what happens to the exponents is that we add them. So we're going to get e to the I 10. Well, actually, I should write that backwards. 10 degrees I plus, or times, plus 15i. So then, if you combine the like terms, you're going to get 25 degrees I, which is the same thing as de Mornay's theorem, where you take the two angles and you add them. So as an exponential, it's just natural to add the exponents, and there's nothing to memorize. The only thing you have to memorize is that you can change cosine theta plus I sine theta into EI theta. It also helps out if you're doing division. What if we were doing cosine of 30 degrees plus I sine of 30 degrees divided by cosine of 50 degrees, I sine of 50 degrees. Oops, I forgot the I. Then if we change these into Euler form, you're going to get E, and I'm going to put the degrees first, 30 degrees I, over E 50 degrees I. And here, the natural thing to do with the exponents is subtract them. So you're going to get 30 minus 50. So this becomes e to the negative 20 degrees I. Now, negative 20 degrees is just a weird angle. Calculator-wise, it'll work out fine. You just got to be really careful with putting the negative in there. Me personally, I like wrapping it around and make it 340 degrees. But once you get to this e negative 20i, then you can expand it back out into cosine negative 20 degrees plus I sine negative 20 degrees. And that would be your answer. And if you wanted to convert it back into like numbered numbers, you could just do a calculation on cosine of negative 20 and sine of negative 20. One thing to notice, I'm not putting moduluses in here in these two areas. And if you did, all you would have to do is divide the numbers individually and put the modulus out front of the e. All right, here I have two complex numbers, 2 minus 3i and negative 4 plus 7i. And I've designated them as z1 and z2, z sub 1 and z sub 2. So I want to find their product and their quotient, z1 times z2 and z1 divided by z2. So the first thing you should do is at least get a coordinate system understanding of where these complex numbers fall in the plane. So 2 minus 3i is going to be in the fourth quadrant. So I get this, triangle over here in the fourth quadrant. This is 2, this is negative 3. And I'm looking for, of course, this angle and the modulus. So let's go with the modulus first. It's going to be the square root of 2 squared plus negative 3 squared, which is the square root of 4 plus 9 square root of 13. All right, so the modulus is square root of 13. And then we can look for the angle by doing, didn't leave myself enough room here, tan inverse of negative 3 over 2. So let's see here. So tan inverse of negative 3 over 2 is negative 56.3 degrees. And negative 56.3 degrees does put you into the fourth quadrant. So that gives me my polar form of z1. So this is all about z1. z2 is negative 4 plus 7i. So that puts us in the second quadrant. This is negative 4. This is 7. We're looking for the modulus first. So that would be the square root of 7 squared plus negative 4 squared. Order doesn't matter, so that's 49 plus 16. I'm going to go off to the side. That's 15, 65. So that's the square root of 65. Here. All right, and then we'll do tan inverse to get its angle, hopefully. So tan inverse of 7 over negative 4, it doesn't matter where that negative sign is going to land, is negative 60.3 degrees. All right, so it initially gives us negative 60.3 degrees. Now remember, you have to be careful. Negative 60.3 degrees is down here in the fourth quadrant. So if this is still negative 60.3 degrees, we need to measure this angle. And that's going to be 180 minus that. So basically, I'm just going to add 180 to this, because there will be opposite signs, and therefore we're going to subtract. So the angle that I'm interested in, this one, by the way, over here is definitely theta, is 180 plus this angle. So let's see here. Plus 180 gives us 119.7. And that'll be our argument for the second z. All right, so if we're going to do a product, I'm going to change both of them into Euler formula. So this one is going to be the square root of 13 e to the negative 56.3 degrees. If you want to make it positive, that's perfectly fine. Add 360. And then you're going to put the I. The other one over here, I'll do it in a different color, is going to be times the square root of 65 e to the 119.7 degrees I. So if I'm multiplying, I'll just multiply the two radicals, square root of 13, square root of 65. 13 times 65. So it'd be the square root of 845. The square root of 845 e to the negative 56, 19.7 minus 56.3. We'll see if I did that right. For our angle, 63.4 degrees I. And that would be multiplying them together with Eulers formula. And then we can spread it out as Trig form. 845 cosine of 63.4 degrees plus I sine of 63.4 degrees. All right, so you think you're done? Well, I'd like to know what this is with just numbers, because we started off with 2 minus 3i and negative 4 plus 7i. So let's see here, 840, 13. Don't know if it's plus or minus, so I'm not going to write that just yet. So I just need to change this into sine. And we get 26, about 26. So it'll be plus 26i. And if you multiply them out by hand, you should be getting 13 plus 26i exactly. Remember, we're just running into rounding error when we do our calculations, but it's really close to 26. I'm not sure if you can see it, but I did the calculation up here, and it did indeed come out to be a perfect 13 plus 26i. All right, so let's do the quotient part. Now, the quotient part, very similar. You're going to do square root of 13 divided by square root of 65. And I'm just going to leave that alone as an ugly number, the square root of 13 over 65. Technically, you're supposed to rationalize it, so it would be whatever the heck 65 times 13 under a square root in the top, all over 65. It's just messy that way, I think. So then it'll become times, e to the. Now, because they're division now, we're going to take these two powers and subtract them. So this is going to become negative 56.3 degrees minus 119.7 degrees. And this might be the case where if you did change this into a positive answer, it might have made our lives a little bit easier at this point. But let's leave it the way it is right now. So negative 56.3 minus 119.7 gives us a negative 176. And if we want to make that positive, we would just give it a full rotation. So I would add on 360. And it just makes the number look a little bit nicer, 184 degrees. So then this becomes the square root, This becomes the square root of 13 over 65 times e to the 184 degrees I. And then we would expand that out into trig form. So this would become the square root of 13/65. That square root covers the whole thing, there we go, times cosine of the angle, 184 degrees, plus I sine of the angle, 184 degrees. All right, so let's see how close this is to the real answer. So I'm going to distribute this ugly number to both of those terms. So if I multiply square root of 13 over 65 times cosine of 184, I'm going to get negative 0.45. All right, so negative 0.45 for the real term. And then if I do the same thing for the sine, I just need to change this cosine into sine. I'm going to get negative 0.03. Negative 0.03, and the second term gets an I. So down below here, I've actually done the calculation, old-fashioned style, multiplying top and bottom by the conjugates. I've FOILed out the top, conjugated the bottom, and we get negative 29 over 65. Negative 29 over 65, we're getting 0.446, which is almost exactly what we got earlier for this piece here. And then the negative 2 over 65, we're getting negative 0.03, which is really close to what I got in my second position. So this method will get us to the right answer. Now, is it the easiest way to do this? No, this is preferable for division. The other example I showed you is preferable for multiplication. The problem comes when we start raising to larger powers and taking roots of a complex number. So now we know that multiplication in trig form and Euler form and division pretty much work fairly well. And the reason we need to know that is if we want to find negative 3 plus 4i to the fifth. Let's not go too crazy. And so we're going to go through the same steps, but I do not want to write this out 5 different times and then multiply 2 of them together. It just gets too messy. So let's figure out what this is in polar form, trig form, and Euler form, basically from one picture. So negative 3 plus 4i is going to plot in the second quadrant, and we're going to draw our triangle. And this side is going to be negative 3, this side is 4. The hypotenuse, by the way, if you do Pythagorean theorem, that turns out to be 5. It's a Pythagorean triplet, 3, 4, 5. All right, so the next step up is to find the angle. And of course, the angle that we're talking about is the one that starts at the positive x-axis and ends in the second quadrant. So to do that, I'm still going to have to do tan inverse of 4 over negative 3. Now, this is not going to be the angle up here, not theta. We're looking for whatever the heck the calculator is going to tell us this is. So tan inverse of 4 over negative 3 is about negative 53.1 degrees. So negative 53.1 degrees. And again, that's a problem because that's down here in the fourth quadrant. So to get to the right answer, we just have to add 180 degrees. All right, so theta is going to equal, add 180, 126.9. So 126.9 degrees. All right, so polar form is going to be 5, 126.9 degrees. I'm going to skip trig form and go right for Euler form. Euler form is going to be 5e to the 126.9i. All right, now this is the negative 3 plus 4i. So what we need to do to negative 3 plus 4i is raise it to the fifth power. And then again, we're going to use laws of exponents. So the first thing is, there's a time sign here, so we have to raise both of the terms to the fifth power. So this becomes 5 to the fifth power times e. And then when I raise this thing to the fifth power, we have power to a power which we would multiply. So 5 times 126.9. Let's see here. Take this whole thing and times it by 5. So 634. Now remember, this is an angle. So what we're going to do is make it a little bit smaller. So I'm going to subtract 360. That's legal because it's a coterminal angle. And once it gets less than 360, that's the angle I want to use. So 274.3. 274.3 degrees I. And at this point, I can expand it out. I'm going to leave it as 5 to the fifth times cosine of 274.3 degrees plus I sine of 274.3 degrees. And then this would be the answer after you expanded 5 to the fifth times this mess. Sine of 274.3. So that would be 234.3. And then do the same thing for sine. So let's see here. Sine. And that'd be negative 3116.2. Negative 3116.2i. So this thing would represent negative 3 plus 4i raised to the 5th power. So it's really one of the only ways you would want to do this is to change it into polar form, Euler form, into trig form so you can do the calculation and come up with an answer. So here's the worst case scenario. It's a root of a complex number, and it causes some difficulty because it's not a simple answer like multiplying two of them together or raising it to a whole number power. So here basically we're doing 4 minus 3i to the 1/3 power. We're going to start off the same way though. 4 minus 3 will put us in the 4th quadrant. And I'm using 4 and 3 again because it does create that special triangle where this side is just 5. It's not always going to be a nice number, but in this case I just wanted to keep that number simple because the modulus isn't the difficult part. It's that argument that we're going to have to mess around with a lot on this one. So again, we're going to have to find the angle. So tan inverse is actually going to give us the right answer because it's in the 4th quadrant. So this will be theta. So if it's in the 1st and 4th quadrant, we're pretty safe. It's when it gets into the 2nd and 3rd that we have to be very cautious. Generally at 180 degrees. All right, so tan inverse of negative 3/4. I don't know why it keeps dropping the negative. Is negative 36.9 degrees. So theta is equal to negative 36.9 degrees. So Eulers' formula is going to become 5 times e, the 5 of course coming from the modulus, e to the negative 36.9 degrees, I. Now in this case, I'm not sure if I would want to change it by 360 degrees. You can. It'll probably make life a little bit easier, but I'm going to leave it alone and see what happens. All right, so now we need to take the cube root of this thing, which is the same thing as raising it to the 1/3 power. And this is where it gets a little tricky. When we took the last question and we raised it to the 5th power, it really has no effect on the angle being multiplied by 5. It'll wrap it around, and we had to unwrap it one rotation. The problem with division is it makes it smaller than 360 degrees. So we're going to have to pull in that trick of solving equations when you had to divide a number across. And that trick was this. We're going to have to take our angle, negative 36.9 degrees, and we're going to have to add 360 degrees k, because we know that we're going to divide my number by 3. So I try to treat this as if we had an equation like 3x equals 40 degrees. And because we were going to divide by the 3, we had to add on that 360 degrees k to account for all the possible rotations. All right, so this is going to be representation of our theta. All right, so if we divide my angle by 3, divide this by 3, we're going to get negative 12.3. Okay, so theta is going to equal negative 12.3 degrees plus 120 degrees k. Okay. So if k is equal to 0, obviously we're going to get negative 12.3 degrees. If k is equal to 1, we're going to get 107.7. And then if we add on 240, which is 2 times 120, we're going to get 227.7. So these are all angles that we are associated with taking the cube root of this number. I'm only going to figure out the first one, and then I'll show you how to get the other ones pretty simplistically. Well, graphically at least. So we're going to get as our first answer, the modulus is the third root of 5. Remember, we still have to do, let me change colors here, the third root of 5. We took care of the dividing this angle by 3, but we never took the third root of 5. So this would be the third root of 5 times cosine of negative 12.3 degrees plus I sine of negative 12.3 degrees. All right, and then we'll distribute that cube root of 5 degrees. So that'll give us 1.67. I'm going to go 2 decimal places. So this is 1.67. And then do the same thing and just get rid of the cosine and make it sine. And that's negative 0.36. Negative 0.36i. And that is one of the cube roots of the cube root of 4 minus 3i. The problem is there are 2 more. And basically all you would do is put in 107.7 into our sine and cosine, get an answer, and then the same thing for 227.7. Here I did the problem on a computer for this one. So here's the representation of 4 minus 3i, way down here at the bottom. And the root we found was 1.7.4, which would be this point here. So we found this coordinate on the last problem. So if we looked for the other two, for instance, this one is talking about the angle 107.7, which is when k is equal to 1 for our case. That turned out to be this answer up here. So that would be k equals 1, this was k equals 0, and over here is k equals 3. This is the angle. So the k equal 3 here is that 227 degrees down there in the third quadrant. So another thing to notice here is it looks like we've taken the entire quadrant and cut it into 3 equal pieces. And it's actually true that each one of these is 120 degrees apart from the other one. So for a cube root, we'll get a 3 split of the quadrant, therefore 3 answers. If you had a fourth root, it would cut the quadrants into 4 equal pieces, just like a coordinate system, but rotated. A fifth root would have 5 answers, and a square root will have 2. So you know how many answers you're going to get, so all you have to do is go looking for them all.